the road. Someone's gonna hurt you like you hurt me.
I settled in Huntsville because my last tour with Patriot in the Army was here in Huntsville. Doris and I liked the area. It was nice people. It was a nice area. It had enough of, you know, the modern conveniences, but it wasn't with some of the problems of real huge cities, you know.
You got to reap what you sow. And I'm saying it's true. Like you've been streets.
So it was still somewhat a bit of the old South still here and so forth, and so we were very comfortable here, and so we just settled here. I also could get a job here. But that's how we came to be in Huntsville, and of course by then I was working on the energy and all this stuff. In Louisiana, we never got out of the Depression when most folks in the U.S. recovered from the Depression, and so in the 30s, particularly in Louisiana, it was very, very dire times. Many of the old people in Louisiana were starving, literally starving. There were no jobs, very difficult to find any jobs. You could barely eke out a living by working in the timber business, you know, starting before daylight, working till after dark for peanuts. If you were lucky, you could perhaps get a job in the oil field as a roughneck, but you at least made a little bit better salary, so you got more money. If you were really lucky, you got a job on the railroad. My goodness, the railroad had a retirement. But there wasn't the large-scale welfare and the things like that we associate today, the recovery mechanisms. The props to prevent starvation, to prevent a lot of the children dying with disease did not exist. Disease was a big problem in Louisiana in those days. Typhoid, diphtheria, this kind of thing, killed a lot of people, particularly children. My father could not read or write. He never finished the first grade. His father died when he was still a baby, was not walking yet, and he went to work to try to keep the family from starving when he was 12 years old, driving a big log wagon, which is what they used in the woods then, with a team of 8 horses, big horses, you know, or the big mules that logging people use, which is a very strong man's job. It's a very tough job if you've ever tried to do it. And he did it at 12 years old, but he fed the family. He kept the family from starving. And he worked like that all his life. So he had a background of doing nothing but work, work, and that's what he did. That's how he made it. But then we weren't the only ones. There was family after family after family in exactly the same situation. I was hospitalized, for example, with malnutrition, not having enough to eat. Okay, that's the Pepsi-Cola scholarship. Yeah, that was interesting. We're not running, are we? Okay. You can't believe how stupid you can be when you come from way back in the sticks and you don't know anything. You haven't been exposed to anything. See, we all came from way back in the sticks. I mean, about as far as you could get. Big swamp started out behind my house. Anyway, they post this thing on the homeroom one time. The bus would come pick you up and haul you in and haul you back. Such and such time, the following people report to room so-and-so. No explanation, no nothing. Just report to room so-and-so. Well, we didn't question what the orders were. You know, we just did it. So-and-so time, I appeared in such and such room along with the other people, and they were passing out these papers, and it looked to me like it was some kind of aptitude test or something. Nobody ever said what it was or what the purpose was. Sit down, you're supposed to take this test. So we did. I wasn't concerned with it all. Breezed through the thing, handed in, walked out way ahead of finish time. Didn't take any effort or consideration at all. Could care less. So some months later, we're sitting in the assembly towards the end of the year, and you'd had to seen it. I'm sitting there with blue jeans on, tore up, not because it's a fashion, because that's what we had. And another assembly program, in an auditorium, and so, I'm not involved. I'm sitting there nodding, and all of a sudden I get the strangest feeling everybody in this auditorium is looking at me. So I up periscope to see what the hell is going on. And they were looking at me. And the guy next to me, Punch, said, the principal just called your name. Get on down there. And so I'm going down the aisle wondering, what the hell am I going down the aisle for? What's going on or anything? So he's shaking my hand. He hands me this scroll and all. It's the 4-year Pepsi-Cola scholarship. That's what the silly test was. They awarded 2 for each state, 1 to white and 1 to black, and I won the 1 for white for Louisiana that year. I wasn't going to university. I'd never had a chance, Suddenly I could go to university. Well, if you count the military training in Command General Staff College, that's considered the equivalent of a master's degree in military science. And in fact, you can get a formal master's degree there now if you do a thesis. I did a staff study, not a thesis, so I didn't get a formal master's degree, but it's recognized at the master's level in military science. And so I had that, and I had the actual master's degree in nuclear engineering, the equivalent master's degree of a master's degree in aerospace engineering, and lots of missile experience. The shortage of energy, particularly for an emerging country that's got to have it, becomes overwhelming. They have to do whatever they have to do to try to get it. And unfortunately, the conventional forms of energy do not spread uniformly throughout the world. They occur in various places, and those places are not always stable countries or stable areas of the world. For one thing, a lot of conflict over control of the actual resources. A lot of dictators. Things are not always sweet democracy, for example. And so you have a great breeding ground where the mechanisms like oil, for example, and natural gas, the mechanisms that are used for most of our energy today are very, very short or even non-existent in many parts of the world. So what are those people going to do? What are we all going to do when the total need for electrical power industry overshoots the ability to furnish it, particularly with a centralized system? You can only burn so much coal because you only got so much coal. Fortunately, we do have a large coal supply, but it's dirty when you burn it, much dirtier than natural gas, for example. So the cleanliness of what you're doing gets to be a big problem. If you're in a desperate part of the world and you have coal burning, you don't have any cleanliness. You have it being burnt as dirty as need be. And what happens is you have many more children dying and things like that, lung problems, things like that going on. So energy is a thing with insidious. It's embedded in our society in everything from the health to the economy to the strength, the ability to maintain the strength, for example, militarily, to keep yourself free and keep from being overwhelmed and suppressed. Energy is involved in everything, to have a decent standard of life. You don't have it if you don't have cheap, clean energy, at least cheap energy. We would hope cheap, clean energy. The energy problem touches every human being on this planet. It touches whether or not we have energy wars and whether we decimate whole areas and whole cultures, or whether we can, in fact, turn to alternative sources that allow it to do it cheaply and cleanly and easily. And we need some work, yes, in windmills and solar cells and all of that. We need everything we can get, but they alone will not do it. We have to go to energy from the vacuum. That's the only alternative we have. So what are we going to do? Well, we're going to turn to our scientific community and we're going to say, what can be done? Our scientific community, unfortunately, is going to tell us the only alternatives you have are the ones you're already familiar with. You can burn more coal, you can build more refineries, you can build more pipelines, you can drill more oil wells. More of the same is all you can do. You can help some by building more windmills, windmill-driven power systems, by closely taking advantage of your hydroelectric capabilities, by particularly solar cells in areas where the solar radiation will support that. But these can only help around the edges. But say, if they're 15% contributors, if you can make them 15%, well worthwhile doing it. But the brunt of it today is going to be oil, natural gas, coal, and nuclear power. That's exactly what the brunt of it has got to be taken by. And this is what we're facing. This leads us to the large centralized power system. The terrorist threat can lay it down anytime it wishes to. And we can turn around one day where the very thing we've done to supply us with energy goes right out the window and right down the tube. So we're caught between a rock and a hard place, in the old saying. We're damned if we do and we're damned if we don't. There has to be an alternative. The alternative has to come from the scientific community. We've got to go, for example, take electrical engineering. The model that is used in electrical engineering is over 100 years old. It still assumes a material ether. It's a useful model. It's done a lot of things, but it's got a lot of problems. It still assumes the old material ether because it still assumes a force field in space. There's no such thing. We've known that for decades in physics. Nobody has ever changed that model. Not one. It still assumes, for example, that the vacuum is inert. In particle physics, my goodness, since at least 1930, the year I was born, we have known that's false. The greatest energy reservoir in the entire universe is what we call empty space. Our physics proves this. We don't have to go reprove it. We have to go back into our models, back into all the equations we've gotten so comfortable with. We've got to look at their assumptions. First, let's talk about the modern view of a charge, because it differs appreciably from the old classical view that we've used so long. The modern view of the charge considers the charge and its interaction with the vacuum at the same time. It doesn't consider a charge sitting off with no vacuum, no space, or anything going on. It considers that interaction. So if I have a charge sitting out here in space, a so-called isolated charge, it's not isolated at all. First of all, what is actually here? What is here is a very strange thing. The vacuum itself, as we said, is full of bubbles, little virtual particles bubbling up and down and appearing and disappearing at incredible rates all the time, jillions of them. So let me draw some dotted circles here to get some bubbles, little virtual particles that appear and disappear very, very rapidly. And all around here, all around this charge in isolated space, let's suppose this is an electron, so it has a negative charge. Then around it in space are all these little positive charges that bubble up and favors that. So I got a little positive, little positive, little positive. Each one is momentarily, but they're replaced by another one right after. They're all over. So we got these positive bubbles. What we say is that this charge has polarized the vacuum. That means opposite charges now are clustered all around it. All little bubbles filled that are positive charges. So I have a negative charge here in the middle, surrounded by this tremendously dense shield of positive charges, virtual state charges. Little bubbles that appear and disappear with great rapidity, but they're positive. So what I have is a very strange thing. If I'm outside this now, trying to look into this charge in the center, we call this the bare charge. What's really in here in the middle that we really never can see because we're seeing through all this shield. I actually see a difference between what the bare charge is in the middle and what this total charge is around here. I see through this charge by whatever goes through here. Ironically, it turns out that the bare charge in the middle is infinite and has infinite energy and charge. These charges are also infinite. They have infinite energy and charge. But the difference between the two infinite quantities is a finite charge. And that's the value that's in the classic textbook. It's what we see and our instruments see and measure through all the shield of an infinite bare charge in the middle. So we're looking through one infinite charge at another one. And as we said, there's no shortage of energy here because we've got two infinity charges, and so we've got plenty of energy. We've got an infinite amount of energy. So this is the way a charge actually exists in space today, as we know from particle physics. We have experiments that show this is the way it exists. We have not just the bare charge in the middle, but this tremendous charge around it, and we see the difference. We'll see it as an electron, and the charge of an electron that's in the textbook is the difference that we see between these two infinite quantities. So already when I say an electron, I have already introduced infinite charge, and I have already introduced infinite energy. This is the thing to realize. It's not in electrical engineering. The difference is finite, and it is the classic value that our instruments will record. They take the difference of what you can see. So now we want to look at what we call a dipole. A dipole is nothing in the world but two charges that are opposite and with a separation between them. So if I have a negative charge here, let's forget the infinity for a moment, and a positive charge out here, I have a dipolarity because I have a positive charge on the end of one length, of a little bit of a length, and a negative charge on the other, and that's what we call a dipole. A dipole, simple dipole, would look like this. We would have in the middle, or on one end, we would have one charge. On the other end, we would have the opposite charge. Let's call that a minus and this a plus. And the charge is sharing effects, polarizing space, curving space-time, all of that good stuff, each to the other one like this, and then off out into space every which way like this. In other words, we have actually caused a change in the entire space-time here, and it actually reaches to infinity in all directions. But there's an interesting thing about this dipole. Once I have opposite charges with a little bit of separation, in 1957, the great discovery was made called broken symmetry. The mathematicians were all chasing beauty at that time, symmetry and beauty. And for a long time, physics didn't want to even hear broken symmetry. That's what you had a Nobel Prize given in 57 to Li and Yang by actually proving, suggesting very strongly certain interactions had broken symmetry. And Wu and her colleagues jumped on it and in less than a year proved it experimentally. Mm-hmm. It was such a revolution in physics that the very year that Wu and her colleagues proved it in February, they awarded the Nobel Prize in December that year to Li and Yang. Unprecedented speed of movement. Broken symmetries and all this bubbles we're talking about, instead of them all zeroing out, a broken symmetry gives you something that's not zero anymore. Or as Lee said, noblest Lee, something virtual that you can't see and can't observe has become observable, that your instruments can see and measure. Something real has been born out of this pre-state that's virtually real but not observably real. So opposite charges, any dipolarity, is already proven to be a broken symmetry, both theoretically and experimentally. We don't have to reprove that. This is not in electrical engineering. Broken symmetry in this fierce energetic flux of the vacuum means that just because we have these two charges in this position, they don't have to do anything, we don't have to do any work or anything. They constantly absorb these, what we call virtual photons, some of these bubbles. As they absorb an individual bubble, it's still not observable, but it makes a little change in the virtual state. Let's call that, in terms of mathematics, that would be a little differential of mass. It changes it to mass when it absorbs a photon. So that's a little dm1, the first one. The next one that's absorbed, and this goes going at an incredible rate, is a little dm2. And as these things continue being absorbed, the amount of mass is increasing differentially until that amount of mass, if it were converted back to energy, would be equal to the energy in an observable photon. That's what we call the quantum threshold, when a real observable photon can be born. Interestingly enough, as this thing roars up through the quantum threshold, this fierce buffeting that it's taking from all these particles of the vacuum being absorbed and beaten on it, kicks out that observable photon. Just beats it right, just kicks it right out of there, collapses this excited state it had reached, and it starts all over again. So this thing is cycling. It's at an incredible rate. It's going up, pow, releasing a observable photon, coming all the way back down, going back up, pow, another one. And so photons, real observable photons, from this isolated classical charge in the classical view, if I have a source charge here, because it has polarized the vacuum, there's really a whole big set of dipoles that we drew over here. This ensemble, this dipole ensemble that really is what's going on between the charge and its vacuum, is continuously radiating real, honest-to-God, electromagnetic energy at the speed of light, photons, in all directions, continuously, free. I don't have to do a thing. I don't have to put in any energy. I don't have to do any work, but let the charge alone. This is what the classic guy would call this an electron, let's say. But if I put what the vacuum is doing, I had all these positive charges out here, so I had a whole big set of dipoles. And this set is radiating energy right out of this charge as real, honest-to-God photons in all directions, continuously. Now, what this means is, here's a photon on its way at light speed. Right behind it is another one. Right behind it is another one, in any direction I make. And so there's streams of photons flowing in all directions, and we're back to Tom Van Flandern. We now have our unfrozen waterfall that appears static. The field appears static. That's made of all these moving photons. But every part of that field, of that E field that's around here, for example, or of the potential that's around here, every part of it is moving at light speed and continually replaced by the photon coming along behind.
That previous drawing of the dipole, where you're talking about you have DM1 and DM2.
Yes.
At what rate are those occurring into the...
An almost unthinkable rate, so fast that we couldn't even calculate it. What we can calculate is the rate of flow, because we can measure that. We can measure at a certain distance the rate of flow of the photons coming through. And we can set up measurements. We can measure what we call the intensity of the field. That's, you might say, the intensity of the photon flux at this area. As it's spreading out, there's less flux out here. The intensity is less. but it goes on out towards infinity. The moment this charge is born, created, this process springs into being from the vacuum, and it continues thereafter as long as the charge physically exists. For example, the original charges in the original matter of the universe, which are still with us, a lot of the original matter is still around, has been doing this and pouring out electromagnetic energy, real, honest-to-God electromagnetic energy for something like 13.7 billion years. So it's not likely to run down in the future. They really don't know what the Big Bang was. There are various theories of the Big Bang. There are theories that say you didn't have a Big Bang. There are all kinds of inflation theories and takeoffs on this, and what we're doing here, we don't have enough real, honest-to-God experimental data yet to where we can differentiate between the basic theories. As things swing one way, the pendulum swings one way, we'll think, well, maybe this theory is correct, and it'll start to swing the other way. And the truth is, we really don't yet know what started it all. The prevailing sort of standard idea is there was a sudden inflation of energy, all of a sudden, very great inflation that started it all off, and it's all been expanding out since then. But we really don't know exactly how that happened. Practical dipoles, permanent magnet. Magnetic charge we call a pole. So if I have a permanent magnet sitting here with a north pole on one end, a south pole on the other, that's a positive charge and a negative charge, magnetic speaking. This dipole has to exhibit the broken symmetry of opposite charges. And this dipole is steadily pulling energy out of the vacuum, pouring it out at a steady rate. This is not a static system. It is a non-equilibrium steady state system like Van Flanderen's waterfall. And every part in that field is in continuous steady motion, but it's being replaced as it leaves by one right behind it. So at any point in space outside here, the intensity of the flux flying through here stays the same, just like that waterfall. So we have what we call a static field. The picture of the field seems to be a steady state thing, and we call it static, but it is not. It's a steady state, dynamic state. The continuously flowing energy at all times. And so a permanent magnet, as silly a thing as a permanent magnet that we can make on the bench, once we pay to make it, if we'll leave it alone, it steadily radiates electromagnetic energy from now to as long as that magnet stays there. Our problem is we have never decided to go in and find out how to extract the energy from this flow without messing with the north and south pole or without killing the magnet or something. We haven't actually found out how to seriously tap a non-equilibrium steady state electromagnetic flow of energy. That should be the greatest problem that we're working on, exactly how to do that and not mess with the dipole. It puts out pure electromagnetic energy. Now, let me quote what the leading electrodynamicists of the day will tell you. The distinction between an E field and a magnetic field is just a bit arbitrary.
E field being?
Electric field. So if we move just right one way, we'll see part of the E field as a magnetic field. If we move the other way, we'll see part of the magnetic field as an electric field. And we really should always say the entity itself is always an electromagnetic field. It's how we observe, how our observing conditions are. So it's not too much stretch to say, I don't care whether it's a magnetic field or electric field. It's really a combination of the two. So the point is, it does produce energy from the vacuum. We don't have to go find a magic method of how to extract the energy from the vacuum. Nature tells us, and physics tells us, if we will look at the broken symmetry of the dipole. And we realize that the isolated charge in classical theory, in modern theory, is not an isolated charge at all. It's continually taking energy from the vacuum. It's a dipolarization, takes energy from the vacuum, pours it out as real energy. Our problem is to catch that real energy and not mess with the dipole and use it. Put a bucket out, catch a bucket full, and use the bucket to power the load. Don't go kill the dipole. Broken symmetry was, in fact, this flux here. If I didn't have the charge placed in here, then all I would have is bubbles, and they'd be equally positive and negative on the average because they're so fast, and in the slightest length of time, they average out to zero. So it appears to be no charge in the vacuum at all. It appears to be nothing there. But there's really continuously positive and negative there, but bubbling away like mad in a fierce cauldron. Incredible energy. That symmetry is when it stays even. I've got plus and minuses equal. But you see, I'm not separating and holding a group separate and holding them intact as negative and holding them intact as positive. If I do that, if I put in something which is not equal and opposite right together, like I put in this negative charge, then it equalizes out by polarizing the vacuum. And what I have now is I have a whole set of dipoles that are pulling energy out of the vacuum, forming it up into quantum-sized chunks called photons and spitting it out. And this thing will pour out this energy just like a gushing oil well that hit a gusher as long as you leave this charge alone. These are virtual states. The little bitty dotted circles are virtual state charges appearing in the vacuum. Now you got more positives, you see, than you don't have equal positives and negatives. You have a predominance of positive appearing. And the combination of the two is a special kind of dipolarity, and therefore it means it's pulling virtual energy and absorbing it, rolling the biscuit dough up into a bigger biscuit and spitting it out in chunks called real photons that our instruments can measure and make real fields and real energy. It's usable energy, but we must accept it in the form that nature gives it to us. Nature gives it to us in a steady state flow out of this assembly here. It takes it from the virtual vacuum, right out of space itself, right out of the vacuum itself, the bubbles. It takes that energy, forms a nice chunk that'll make it observable and usable in our world, and spits out the chunks at you, giving you your normal electromagnetic fields and potentials. Real, honest-to-God physical photon that your instruments will measure and then register, and you can count them and everything else. From the virtual state. You see, nothing is a very unusual thing. You've got to specify what kind of thing you're specifying the absence of when you talk about nothing. If I have the absence of observable thing, I have the presence of things which are not observable, but they're still there. So we have plenty of things which are non-observable, and they are real. They make all the forces of nature. But when they interact with matter, they produce the real forces that change and twist and operate on matter and do everything in the universe. The matter of a photon comes from the fact that if you just compress energy by the factor c squared, it turns into mass. That's all mass is. In the modern view, we don't talk about mass, we talk about mass energy. Because it's the same thing. That's why when you have a so-called looking empty space and you hit it sharply with some energy, you can pop some real electrons out of that space, leaving holes. If you added enough energy, it quit being virtual and it suddenly got past the quantum threshold and it turned into a real electron. If we have a piece of space, empty space out here, about the size of the tip of my little finger, 1 cubic centimeter, all of these bubbles that have such fierce energy, this is the fiercest bubbling that the mind of man has ever conceived. They are so energetic in just that little region of space-time right there, that if I could take that amount of energy and compress it so that it turns into mass, compress it by c squared, I would have more mass than the largest telescope we build today can see in the whole universe. That's how much incredible energy is in the tiniest bit of vacuum. So the electron, when it's pouring out something we call a normal field or a normal potential, it can run with that forever. It doesn't even miss the pocket change to put that out. All we have to do is figure out how to catch the energy. It's already there. It's already transduced from the virtual energy of the vacuum. We don't have to transduce it. And nature has been wonderful. Nature has given us these little engines called charges, which do that. But we haven't been smart enough to apply, let's just catch the flow of energy and don't disturb the gushing oil well. We're trained to go in, and if we start using any of the gush, we use half of it to tighten the screws down and stop the flow. So then we got another set of guys that come in and do something else to unwind the thing and let the flow start again. When we energize a circuit, what we actually do, how we actually power an electric circuit, not what the textbook says, forget that, that's 100 and something years old. Suppose I have a generator. I'm going to very crudely draw a little generator here. And of course, I've got a positive pole. I'm going to put that positive terminal, and I got a negative terminal. And I've got a rotating generator here that's rotating around inside. And I crank the shaft out here. My job is to crank the shaft and turn it. What happens when I crank the generator? I do mechanical energy input, and I have to do work because that's not what I want. I want a rotating magnetic field. So I have got to turn this shaft rotation mechanical energy into magnetic field energy. That requires work. That's why I have to crank the shaft. Once I get the magnetic field energy inside the generator, here are the lines going out from the generator to the whole power grid and feeding jillions of loads for 100 miles. Where does the magnetic energy go? It doesn't leave the generator. Doesn't go out on the lines, doesn't go power any loads. What it does inside the generator, it pushes the positive charges, and suppose this is the positive terminal, this is the negative. It pushes the positive charges this way up to that terminal, pushes the negative charges that way. It separates the charges, which does a little kink in the space out here and makes this plus and this minus. It makes that entire vast circuit dipolar, a dipole, a whole set of dipoles. And every place, once we have this dipolarity, all along here we're extracting energy out of the vacuum and it's pouring right on down the circuit. But the energy is not coming from what we crank the shaft of the generator from at all. Once we make the dipole, the energy is coming out of the vacuum to the dipole. Here's a dipole, here's a dipole, here's a dipole, here's a everywhere dipoles. So we're having energy born in the circuit everywhere in this dipolarities from the vacuum. The biggest dipole is right here in the generator. Okay, we go out here and now we call this progression of dipolarity, we call that potentializing the circuit, making a potential between these two lines, a difference in potential. As we potentialize this circuit, we create little force fields which push the electrons forward as current, push it through the load, and we dissipate some energy in the load, power the load. We lose some in the losses and so forth. But all of that is free except we have now wired the generator in to the external circuit. Any current that moves this way has to move this way. So what we have is from this pole, this positive pole, around through the circuit to this point on the grounded side here, let's say this is the grounded side, the voltage is exactly the same as the negative of the voltage going up the other way, against the EMF. So we make all the current that goes out in the losses and the loads, we make equal current to go back through all these separated charges that we paid such hard labor and money to separate, knock the charges out of there and destroy the dipole. The moment we destroy the dipole, we lose the flow of energy from the vacuum because now there's no broken symmetry. So we have to crank the shaft of the generator some more, turn it a little bit more, make some more magnetic field energy so that we can make the charges move back apart and restore the dipole and cut the vacuum energy flow on again. Whereupon the silly circuit, this closed current loop circuit, uses half of everything it catches of free energy to destroy the dipolarity. So we pay the power company to engage in a giant wrestling match inside its own generator and lose by continuing to destroy its dipolarity and the source of vacuum energy faster than we allow it to power the load. It's the stupidest circuit that anybody could ever originate in powering systems. But it's nice and well behaved because it shorts out everything that wouldn't be well behaved, and it forces that thing to be under unity. You will always have less power in these loads, all told, than you have to keep cranking into the shaft of the generator. And it's responsible for destroying much of the biosphere, polluting everything, and all this. We don't have to do it that way at all. If we make the dipole and stop and leave it alone, do not let any current flow in this circuit here while we're collecting the potential. Just let them potentialize. Once we have the potential difference, switch away this generator, get rid of it, disconnect it, connect the diode, for example, that would only allow a flow in one direction. And now the energy, the excess energy, can discharge by only making the energy flow until it dies. And that energy now can be used to power the load for free except for switching costs. You pay a little to switch, you get a lot of power in your load, you're now off of the leaky diode, the leaky pipe method of powering things, which the closed current loop circuit forces on you. and you're down to the triode method. Pay a little bit for the grid signal and use a lot of energy in the load. You're now into COP greater than 1 systems. So that's the way we ought to be doing electric power. We ought to be taking nature's lesson to heart. Leave the dipole in static configuration with no current flowing through it. It will radiate energy then forever. It's a perpetual energy generator. It's converting virtual energy of the vacuum into real, honest-to-God energy and pouring it out all the time. For you, then, to turn your grad students loose and your sharp young postdocs loose with some funding and time and study to determine real good ways to catch and use the steady flow of energy without destroying the dipole in the generator. You do not have to destroy the dipole in the generator. We have always done it that way. And as long as we do it that way, a century or so ago, the same old way, we will always guarantee that we keep burning all the oil and burning all the coal and polluting the earth and building all of the big pipelines and everything with the centralized power grid and everything we do.
How in the world can you create a dipole with voltage?
A voltage is between a dipole. What you have when you have a potential difference is between these two charges. The two are the same thing. Any potential difference is a dipolarity.
Then explain to me how you can build something that doesn't dissipate its own.
Take an electret. An electret is an electric dipole. It doesn't allow any current between there to knock the dipoles out. So you think, well, I've got a static field, and electrical engineers are trained you can't do anything with a static field. They are not trained that it is really a steady state flow. They're looking for a dynamically varying flow. They're not looking for non-equilibrium steady state flows. And they haven't got the foggiest notion how to catch and use the energy from a non-equilibrium steady state flow. Current has nothing to do with energy. Current is always involved when you're dissipating energy in the loads and losses. It has nothing to do with adding energy to the circuit. Adding energy to the circuit's free. That is just regauging. Guaranteed by the gauge freedom axiom of quantum field theory, you can have all the energy you want free. You can change the potential energy in this circuit anytime you want to for free. It doesn't cost anything just to change voltage. Now, if you let the current flow while you're changing it so it's destroying the dipole, now it's costing you. Because you're losing part of your flow all the time. It's steadily diminishing and you'll squelch it off. Then you got to crank the shaft of the generator some more. But we are not taught in electrical engineering or any of our universities, even in the physics courses, we are not taught what powers an electrical circuit. It is not what we have in the textbooks today. If we go to particle physics, we can put together the dipolar picture taking the energy from the vacuum, and then we know what powers the circuit. It isn't cranking the shaft of the generator. And it isn't dissipating chemical energy in a battery.
The generator creates magnetic energy.
A magnetic field. You had to pay for that because you changed from mechanical energy form to magnetic field form. When you change the form of energy, that's work. You have to work to do that. You're going to have to pay for it. That got away from you. You don't have control of it. But you got the magnetic field energy generated, at least with some efficiency. Maybe a really good generator, a big one, can be 90% efficient, for example. So maybe I only lost 10%, so I still got 90% of whatever I put in. Equal amount of that now magnetic energy that I changed. Okay, this energy doesn't go out on the circuit, doesn't power the circuit. It works on the charges inside the generator. Now they're connected to charges in the wall, so if I push on this charge, I push on all those charges in that line. If I pull on the charge or push on the charge on the other line, I push on all the charges in the line out there. And once I get those things pushed apart inside the generator and have a dipole, I have energy flowing for free from the vacuum. I'm not turning the shaft. I have no more magnetic field energy. This dipole will pour out energy from now till the end of time if I don't destroy it. But as long as we leave it wired into the circuit, and once the current starts flowing, not only does it flow out through the losses and loads to lose some in the losses and then power the loads, but the equal current flows back in the return line and flows through both ends of the dipole the wrong way, does work on them to knock them back out of there.
Why is it if I have Hoover Dam, and I get all those turbines going, and I get all that magnetic energy converted to electrical energy, I create a dipole, I'm powering Denver, Why can't I just turn Hoover Dam on?
You could if you wasn't destroying the dipole of the generators all the time, but the circuits you wired back to the generator is steadily destroying the dipoles that are furnishing the energy to the circuit. The only way you can get any more energy flowing is you got to restore the dipole. You got to keep cranking the shaft of the generator. Because you wire the so-called external source into the circuit and leave it, and let the circuit spend half of its freely collected energy that actually was extracted by that dipole from the vacuum, half of it uses to do nothing but destroy that dipolar and shut off the energy. It's a function of the closed current loop circuit when you wire in the external source. And every engineer is trained that that's the only way he can build a power system, and it's the stupidest circuit that ever was put together if you really want to do power and take it from the vacuum. Now, if you want to keep burning all this coal and making money off of that and trains that haul it, and you want to build pipelines and have big tanker fleets of hauling oil and all this mess and polluting the biosphere and all that mess, then you do exactly what they're doing today. And it will guarantee that flow of money that you're milking from the world will continue to flow to your pockets. The alternative is to turn our young grad students loose and let them, number one, clearly show and change electrical engineering to show how the circuit is really powered. Go back and retrieve Krone's work where he already solved this problem at Stanford University in the 30s, force that out of there and get the way to do his negative resistor, where you can disconnect the generator once you get the thing going, and it will continue to power itself. Let's talk about self-powering. There's two ways that you can have over unity. Let's talk about both ways. I'm going to compare this to a heat pump. Here I have my system. All right, I have my own input of energy, let's say, in this system that the operator inputs. Energy input by the operator, E-op. Okay, this system has some losses. I'm going to put my losses out on the bottom just as one little arrow. It's losing energy all the time in its inefficiencies. Let's say this is a pretty poor system. It's only 50% efficient. Like a heat pump is about 50% efficient. So all of the energy that's going into it from whatever source, 50% of it's going to leak away and escape, and I'm not going to be able to use. Over here now, I have the energy that's going out into my load and powering it, and this is going to be the work output. The actual work that I get from this system that I'm using. Now, if I have a system that nothing else puts any energy into it, this could be, for example, an electric motor. Here's my line energy that I connect and pay the power company for, E, operator input. Okay, I lose 50% of it down here. If I put in 1,000 joules of energy, I get 500 joules of work out, useful work in the load, and I lose 500 in the losses. This is the losses in the system. Every real system has losses if it's doing work and so forth. Every working system will have some losses. They can be made more efficient, yes, but they will have losses. They're not 100%. Well, that doesn't look so good. I'm not getting as much work out as I'm having to pay for energy. I'm only getting half out. This could be a heat. If this was a heat pump, it wouldn't be worthwhile putting in a heat pump. This is a heat pump when I lose the ability to use the atmospheric input and I have to go on to resistive heating. This is what I got. And it's only 50% efficient, and I'm paying through the nose for only getting out half of what I put in as useful work in the heat pump. But we don't do a heat pump that way. From the environment out here, there's heat energy and all this out here if we take it out. So we have a process which takes out some of that energy from that active environment. Let's call this the environment input. Now we have a different situation. Let's talk about how much total energy we have going in. We have two inputs of energy. We have the input that I'm paying the power company for. We have the input that I'm not paying for. I'm paying so little that let's consider this part of it is free from the environment, the heat energy I'm extracting from the environment. So I have these two energy inputs. And by the way, I extract a lot of heat energy from the environment because I compress it and take a lot out. Well, isn't that interesting? Because now if I have 50% efficiency, I lose half of all the energy that goes through the system. Suppose I put in 3 parts. So I got 3 plus 1, I get 4 parts in here. I lose half of that, I get 2 parts out. This is a little bit of bad conditions for a heat pump. But I'm getting twice as much out as I'm having to put in. Now, I'm not violating conservation of energy. That energy is actually being put in to cover these losses and cover the extra energy put out more than half of what I put in. The average home heat pump under good conditions produces 3 to 4 times as much energy out as actual useful work as what you have to pay for. The rest of it comes out of the environment. Okay, let's look at a particular example. I'm going to talk parts of energy. So everybody knows a part is a part. So if I got 1 part, that means something. If I got 10 parts, that means 10 times as much. Real easy. But I'm going to use 1 and 7. 1 part of energy I'm going to put in is electrical energy from the power line. I got to pay the power bill for that. No question, I'm going to have to pay for it. That's on the meter. And the meter's running. Okay, the environment, let's say, and this is a pretty well-designed heat pump, the environment's going to put in a good case, 7 times as much, 7 parts of energy that I'm going to get from the environment for free. So what's going into my system? 8 parts of energy. The total input to my system is the 1 that I put in and the 7 that the environment puts in. How efficient was the system? It was 50%. That means it loses half of everything going through it. That's 8 parts going through it. It's going to lose half. It's going to lose 4 parts. From the 8 going in and the 4 that I lost and I can't use, I have 4 coming out that I use as useful work. Okay, let's talk about the difference in efficiency and COP, because most engineers and even many practicing scientists don't know the difference. Efficiency is all the energy that's put into this system by any port, any factor at all. You divide that amount of energy into the amount of useful output you get. Output divided by total input is the efficiency of the system. What's the efficiency of this heat pump? I got 1 that I input, 7 parts that the environment inputs. That's 8 parts that's totally input to the system. And so the total input to the system is 8 parts. I divide the total input to the system by 8 parts, by how much I get, that 8 parts, into how much I get out. 4 over 8 is 1/2, or we express that as percentage, 50%. So the efficiency of this system is 50%. It is not over unity efficiency. Never can you go past 100%. You always are less than 100% in any real system with losses. You can get a good generator that'll do 90%, but it darn sure will not do 150% efficiency. Now, COP is a totally different matter. COP only looks at 1 energy input and 1 only, and that's what you have to pay for as the operator. It doesn't care if something else puts in energy or not. It's defined as you take the total useful output you got, you divide that by the amount of energy you had to pay for. Doesn't matter what else got put in, just what you had to pay for. And that is your COP expressed as a decimal. Let's see what that is. 4 parts out, 1 part in, 4.0. My COP is equal to 4.0. I got 4 times as much useful work out of this system as what I had to pay for in energy. I did not get 4 times what total energy was put in there. I only got half of what was put in there. But I can have an over unity COP when I have under unity efficiency. It's always going to be under unity efficiency. COP is coefficient of performance. It's the total output by what you yourself had to pay for. It's the bang for your buck. Think of COP as how much bang the system will give for your buck, not the environment's buck, but your buck. You're looking for over 1. You're looking for infinity if you can get it. This is an over unity system. The heat pump is a standard garden variety, common system in everybody's homes throughout the whole Western world. And its normal COP is from 3 to 4. A well-designed heat pump will put out 3 to 4 times as much energy as you pay for. It still is only about 50% efficient, it's still wasting half all the energy. All the rest of that energy comes in out of the environment for free. Let's see how to make this system where I have an environmental input. Let's see how to make this system power itself. So let's draw this. Here's my system again. Right now, here's my environmental input. Right here. Here's the input that I normally have to make to get this thing going. This is the operator. This is the environment in. And I do still have my system losses. These are real losses. And let's suppose this system has 50% efficiency. 50% efficiency. Okay, let's suppose that I put some energy in and get this thing going, and the moment I get it going, I have a thing that allows some energy from my environment to start in, and I get it into a stable operation. So I now have 2 inputs of energy. I have the part that the operator puts in to get it going, get it started and cranked up here. I have the part that the environment finally gets to putting in when it gets going real good and steady. Okay, I have some energy going out over here in my load, and this is the work out in my load. Well, the thing that I used, if I have 50% efficiency, suppose I got a pretty good system. Let's suppose that I get 1 and a good number would be 9, say. Let's suppose I put in 1 part to get it going. The environment then puts in 9 parts, and I get a total of 10 parts that would be input during that time into the system from both of those inputs. But it's only 50% efficient. So 5 parts are losses. They get lost from the system of the 10. The other 5 is useful work out. This is what my system is doing when I get it running. Now, clever devil that I am, I have worked out a system to take part of this output here and take it off of here in a clamped and governed feedback. I'm not going to draw all of that. And bring it back over here and bring it up here. Put a little switch in here that I can throw or I can connect right here. So I have the thing connected, my input's going, I get it wound up, I get my 9 points in, my 1 part in, I have 10 parts in, I'm wasting half of it as losses in 5, I'm getting 5 out. Most of the energy is coming from the environment. But suppose the efficiency of this process here, the feedback loop itself, suppose this efficiency is only, again, 50%. To replace 1 part at a 50% efficiency, I'm going to have to put 2 parts available to that subsystem. So just to make a block here where I got my switchers and all that, that's the subsystem. So I'm going to have 2 parts coming off of there, which is going to subtract from my 5 and is going to leave me 3. So I now am only outputting 3 parts from this system, but 2 parts that I saved by doing that, I fed it back over here and I lost half of it. It went down here as another loss. But I got the 1 part back over here that the operator was putting in. I no longer have to have him connected. The generator doesn't have to be connected. I can disconnect it, and the 1 part that's needed to run through that system there is continuously furnished from the output. This is a self-powering system. What's its COP? It's the 3 parts that I have going out divided by 0. I'm putting nothing in myself once it's going and the generator disconnected. This is now a COP infinity system. Are there real systems? Yes. A windmill-powered generator is a COP infinity system. The operator's not putting in anything. He's getting useful output, and he puts in nothing. The wind puts it all in for free from the environment. Hydroelectric power plant, he doesn't put in any energy. The river's flow puts it all in. It's a COP infinity system. Now, it doesn't mean it has an efficiency like that. The efficiency can be very poor, like a solar cell powered system. A solar cell array powered electrical system has a COP of infinity. It usually has a nominal efficiency about 17%. It wastes 83% of the energy. But you don't pay anything for the other 17%. So the point is, you can have a free energy flow coming out of your environment, taking care of the system running itself and powering its load, and you're perfectly within the laws of thermodynamics and the laws of physics. The second law of thermodynamics does not apply except in equilibrium, when you're not having any extra energy coming in. Anytime I have an environmental input, I'm out of equilibrium. This system does not have to obey the second law of thermodynamics, because that's an equilibrium law, only for equilibrium conditions. Check your book. It doesn't apply to non-equilibrium systems. So obviously, if we want to live and do well, we're going to design a lot of non-equilibrium systems. And we're going to shoot for the design of self-powering systems. That's why they build hydroelectric power plants. That's why they build windmill-generated power plants. That's why they build solar cell array power systems, because the energy itself is for free, even if it's a pretty inefficient system. So the COP becomes infinite with real systems working out there today. Now, we can do the same thing with a system that's taking energy from the vacuum if we use exactly the same process. If we crank it off and get it going, and we get enough extra energy added from the environment, it doesn't care what the environment is. If we are taking that energy from that steady flow that will always come out of any group of charges we assemble, and we know how to do that, let's say we worked out how to do it, without destroying the dipole will pour the energy out to it, and we collect some of it. Then we have this system right here, and thermodynamics and physics says it can be a self-powering system. With a MEG, we haven't gone to that stage yet. We're still in the open loop system where we haven't put the feedback. But it's possible to do that. We just are working things out one thing at a time. Here's what we have in the MEG. And here's why we can do it with the MEG legitimately as proven in physics. In the MEG, suppose I have a toroid coil. A toroid is wound around like this in a circle, but it's wound all the way around it very tightly, and it closes back almost on itself. What happens in a toroidal coil is the magnetic field, the B field, is confined inside the coil. It can't escape outside. Normally, the magnetic field spills out all into space. We need to know two things. Magnetic field, any force field, is not a primary field of nature. The primary thing is always a potential, and it's called a magnetic vector potential A. That's the name of it. Magnetic vector potential. Now, a magnetic vector potential is a weird beast. It's got two components, basically. One is swirling. It's a curled component, and we would write that del cross A, and that is what we call the magnetic field B. And normally it hides the other component. It covers it to where we don't see the other component. The other component is one that doesn't have a curl. Doesn't have a curl. It's moving straight. So the curl of it is zero. But it's still a real potential. If you take this toroidal coil, first of all, we had to pay to get that B field trapped. But it's been found by Aronoff and Baum in 1959 that if I normally have a source of B field, and I just draw a dot here that makes B field, it's actually a dipole, and here's the B field spreading out in space, I know that's a curled magnetic vector potential A that I'm looking at, and it's hiding this other component I can't see. It turns out if you'll take all that B field, all that curl component, and pull it back in and hold it in a little area, localized area, so that it doesn't spill out into space, you reveal outside there that hidden component, the uncurled or the curl-free A potential. So isn't this interesting? If you localize the B field into a little small location instead of spreading through all space, you have all the B field energy you would have had through all space. You got that in your hand in this local space, but outside that, you got a whole bunch of extra energy now in uncurled A potential form. Well, A potential is wonderful. In the curl form, it makes magnetic field. So if I've got magnetic field, I got all my curl component down here in this localization zone. And outside here, I have a new component of energy I didn't have to use before in my immediate environment, available. Isn't that interesting? Because it's easy to collect it. All you have to do is change it real fast. The time rate of change, dA dt, produces an E field in the opposite direction from where the A field was going, which direction it was heading. It makes an E field, and the magnitude of this E field that it makes, this electric field, is proportional to how fast you change the thing, the time rate of change. So, now wouldn't it be interesting if I could find a transformer core material and construction which would do localization of the B field? What would I have if I did that? Instead of just looking at the B field in my transformer, I would have the B field now inside the core material. But outside the core material, I would have a new available reservoir of extra energy in my environment. And all I got to do is perturb it, and it'll make electric fields, which come back into the system and introduce real electric field energy into the system, which normally no transformer does. That's what we do with the MIG. We found with this nanocrystalline material they're making for new transformers and all, we found a construction core right off the shelf, type of construction and nanocrystalline material, there's 2 or 3 types that'll do it, that if I make a transformer core material here, I'll draw a simple one. This is just a diagram, it's not exactly the way we structure it. Any source of magnetic field, for example, if I have an input coil here, like this, and I'm paying for the input, all the magnetic field from this coil, all of it, is trapped in this core. It doesn't get out, and there's no spillage out there into space. Interesting. How can I prove that? I put a permanent magnet very tightly across here. North pole here, south pole here. Got to have real good contact, no air gaps of this magnet. It's a very powerful little magnet. It's right across the transformer core material. And then I take an instrument with a field probe to measure magnetic field B, and I put it right on, let's say, that north pole. My instrument measures no magnetic field, or almost zero. It's impossible to get total contact. You will have the tiny, tiny air gap, so you will measure a tiny, tiny field. But essentially a zero magnetic field right on the surface of the magnet. Now that proves that all the magnetic field that normally spilled out of this magnet everywhere has got sucked into this core and is sitting there. When you localize the B field and expose around it that usually hidden uncurled A potential, that's called the Aronoff bomb effect. Aronoff was a student of Bohm. Aronoff. Bohm was David Bohm, of course, as everybody's aware. And in 1959, they published a very formidable and fundamental paper in a physical review series pointing out this effect. When you localize this magnetic field in the space outside this core, not in the core, outside the core, there appears this A potential. But it's the uncurled variety now. It's extra. I didn't pay for it. If you want to put it in proper gauge language, the Aronoff bomb effect gauge transforms the space outside the localization area, which means you see additional energy available there in space itself. That's rigorously proven in the literature. Don't have to reprove it. 20,000 papers in the literature. But it's not in electrical engineering, but it's in physics. The difference here in the MEG is we don't have to pay for what this material is doing. We didn't have to pay to get that extra A potential energy reservoir formed outside the core. That happened free. It's from that regauged space-time, which is a change in that vacuum. It's a result of the fact that this core material will do for free what I got to pay a toroid to do. Only it's free. I don't have to pay for that effect. If I got a toroid, I can get the effect, but I pay for it. I lose everything I'm going to get. I don't have to pay for it in this case. The material does that extra action for me. That's the beauty. Material effects, by the way, are one of those places already recognized in thermodynamics itself as violating the second law of thermodynamics. Material effects, like long-term memory and all kinds of things. Read Prigogine and Condiputi's book, Modern Thermodynamics, that deals with non-equilibrium systems. You will find that that's one of the areas that is known by the thermodynamicists themselves to violate that second law. So I don't have to prove that I'm violating it permissibly. It's already been done by a Nobel Prize winner. So what we have now is, I have an interesting situation. I have what looks like a normal transformer core, but there's a very abnormal thing happening in it. All of the magnetic field B is now confined to the core. And around that, I've got all the magnetic field energy, the swirling energy that I normally have in every transformer. I've got all of that. I haven't lost anything. But in addition, I've got this extra energy reservoir in space just outside the core. And every time I perturb the core, like with my input coil, I put in, clever devil that we are, we put in pulses, sharp rise time and sharp decay time. If I want to get a little bigger E field, I make a sharper rise time and a sharper decay time. I get an E field one direction one time and the other. And what happens is the space here, I can have as many coils wound on this core as I wish. Let's put an output coil on it, just to say we got an output. And it looks like I got my drawing a little bit reversed, but that's okay. There's an output. And over here I got a big load. But in this space outside the core, I'm going to shade the core here so we can begin to see what this looks like. In this space outside where my uncurled A potential is, and I'm going to put a bar over that A to mean that it's a straight moving A. It's not a swirling A. It's not a magnetic field at all. Every time I shake or perturb this A potential, it makes an E field. E equals minus dA dt. And the sharper the change, the greater the size of the E field. From space around the core, this does not happen in any other normal transformer in the whole world, as far as we're aware. From the space outside the MEG, there arises then these tremendously strong E fields which radiate into every coil that's wound on this transformer. So every coil on this transformer that's wound, I could have a dozen coils on here. Every one of them is also, regardless of what other function it's producing, is also an input coil for energy coming in from the vacuum in electric field form, not magnetic field form. The biggest action in the MEG is an electric field transformer, not a magnetic field transformer. And we're using a proven effect, Aronoff-Bohm effect, that 20,000 papers in the literature already tell you happens for real. We didn't dream this one up. We just found how to do it for free. How to get it to happen with the material doing it for us instead of us have to pay a toroid to do it and lose all the advantage. Every coil then has got E field inputs. That's in phase. The funny thing about our output, a normal transformer output will be up towards 90 degrees. It's 85 degrees. It's got some resistance in it, but it'll be like almost pure reactive power coming out of it. That's not true of the MEG. It'll be 2 degrees. It'll be essentially in phase. It's almost pure power, and not a real power, not reactive power. And it's in pulse form. And so what we have to do, We have to add another unit on here, standard technology, to change these pulse forms into a normal kind of power form, like oscillating current or DC current, whatever. So you just go buy that off the shelf from people who are experts and do it very efficiently. But what we really have that's significant, it's not a regular transformer. We have an extra energy input from the environment that we don't pay for. That's the key. Now let's draw the MEG diagram, and it turns out to be just like that crazy heat pump. I have my system called the MEG. I'm going to do the open loop. I'm putting in the operator input. I'm paying for that. Paying the power company, or paying for a battery or something. But now, from the environment, I have this extra input of energy, and I'm going to put the bar over the A, and when I perturb it, it's going to be in dA dt equal minus E. Instead of going out, it's going to come in. So now I have an extra input of energy into my system free from the environment, just for putting in the input I'm putting in. The other part comes along for free. I get that as an extra added attraction. So if I put in one part and I get my input from the uncurled apotential active environment, the E field input, if I get that to be, let's say, 5 parts, be very conservative here. I can make it 10 or 12 or 100 parts, but it'll burn the insulation right off the wire then. So it'll destroy the unit. But suppose I settle for 5, I adjust the rise time and decay time until I get this 5 parts in. Now, coming out, I have input here 6 parts total. The part I put in, I pay for. The 5 parts that the environment puts in, I don't have to pay for. So I have 6 parts of energy coming in here. A normal transformer can be about 85%, 90% efficient. Recapitulating, I pay to input 1 part. The environment is now, by the way we have it adjusted, we make the adjustments in the input until we get this effect, let's say, is putting in 5 parts. And now we have a total of 6 parts, total energy being put in here. Okay, let's suppose this is 90% efficient. Coming out of that, then, I'll have 90% of the 6 parts, which is 5.4. So my energy that I'm getting out is 5.4 parts. Okay, what's the COP? I put in 1, I get out 5.4. Divide 5.4 by 1, the COP is equal to 5.4. I get 5.4 times as much usable energy out as I get in. This is just an energy converter. Now, when I add another stage on here to convert that into a standard kind of power form, either direct current and certain voltage or so forth, AC, I will have an inefficiency existed there. Maybe I'll cut this down. Let's do real bad. Let's cut this down to 3. Let's lose 2 points, almost half of it. We didn't have too efficient a conversion, let's say. We were sloppy. We didn't go get the state of the art. We're much better than that. But even with the bad one, once we have it set to run loads, and actually running loads and lights and motors, we're putting in 1 part, we're getting out 3 parts. We have a 3-to-1, we have a 3.0 COP practical. And that's 3.0. This is a standard achievable thing with the MEG. Okay, then the question that's asked, then why don't you guys have this thing on the market in mass production rolling everywhere? It's a very good question, because let's see why we don't have. What is going on in the MEG that we went through? We pointed out that the E field hits every one of those coils. There's a little bit of out of phasing and everything. They're not all on the same phase. And each coil, once it gets an E field, fires at every other coil, and everything's feed forward, feed back. That's a highly nonlinear situation. And that is the devil and all to try to precisely measure. Trying to measure an individual signal in a dense signal environment is not a simple thing. There are people who can do it, but it requires special instrumentation and highly specialized measurement equipment. Forget your normal oscilloscopes and probes. You can never straighten all of that out. You do it by trial and error and adjust it until it's mostly additive. What we need now is to do all the precision modeling and all the precision work, to work all that out with a math model, to work out the actual measurements and the characteristics of the material, how that affects it and all this. That's 1 year of very hard work. You've got to have 4 specialists in special areas to work with you to do it. We're trying to measure all those exact signals and work out what we would call the transfer function, exact mathematical model for the transfer function of the MEG. If you build those all out of phase so they're subtractive rather than additive, you'll build a worse transformer than a normal. You'll be better off throwing all that away and build a regular transformer. But if you get them additive, you beat the heck out of every other transformer in the world because it goes way over unity. We don't have good control and good models of all of this. What we have to do is adjust everything by hand, and that's not science. We have to keep tweaking the heck out of it. And so what we have to do is a standard, but very interesting and very dense, highly nonlinear control problem, an adjustment problem. We have to have modeling, full modeling for it. We have to have an Aronoff measurement specialist, Aronoff bomb measurement specialist. Those guys are well employed. There's very few of them that know a measurement also. You can get them, but they're expensive. We have to have another person that knows nonlinear oscillation theory, and also we have to have another one that knows nonlinear oscillation control theory. Those are specializations. You don't run down to your local university and your local PhD can do that. The interactions have got to be moved to design and science and modeling rather than fiddling with it. We have a $9 million 1 year job with a team including not only the normal guys, but those 4 specialists we got to hire that are very highly paid, by the way, I might say. And they're fully employed gainfully. They're not looking for a job.
By the way, what voltages are you working with? What level input and what level output? You 5 volts, 10 volts?
Well, normally we try to put something that'll power something, so we're going to reduce whatever we come out with the output voltage. We're going to reduce it to like 120 volts or something like that. Now, we can produce 1,000 volts or 5,000 volts out of this thing and burn the insulation right off the coils. Normally, as an input, we'll use a battery or we put in a circuit in front of it, which is a switching circuit to do the switching to make it oscillate and give us the rise time, get the decay time. So you put in a circuit to do all of that and you adjust and tweak the circuit for the various tunings you want to do. It's a sort of a tuning nightmare almost to get everything properly tuned. But when you properly tune it, it does produce what I've got on this paper. But you can see right away, this is not a simple problem. I don't go get me some transformer guys and whomp up some of these and go sell them. Now, you got your choice about how you fund this. The normal scientific community is not going to fund it. They say you can't do that. Electrical engineering says you can't do it. Forget it. So what you're going to have to do, you're going to have to go to venture capitalists. It's a mixed bag, a mixed breed. There are some good venture capitalists. There's a whole bunch that ain't too good. You cannot work with, as we discussed before, with a government agency. They'll steal you blind and patent around you, all around what you've done. So you're still going to have to go to a risk venture capitalist. You're going to have to convince him that the risk, in fact, justify the investment on the front end. If you look at the risk analysis figures, they're great. How big a payoff is self-powering systems and systems that produce a steady 3-to-1 output electrically? They say once we run it through the hopper, the year that we want to do on it, where we have good models that we can design it in advance, we can put the coils exactly like we need them, exactly where we need them, exactly with what orientation and so forth. Once we can do all of that from the front end, we can build the thing straightforward and put it together and it'll work just like that. You've made it a technology and a science at that time, not a twiddle with it research outfit. We have a lab bench experiment that's successful. We do not have a ready for production device that can be cranked all across, by the thousands and put on the market. We're approaching all the control problems first. We have to do all of that first. Now, in the United States, we tend to be stupid a lot of times. We took nonlinear oscillation theory and control of nonlinear oscillation and made them 2 separate fields. If you use the U.S. controlled system, the guy will have you chasing strange attractors for the next 10 years. If you go to the Russians, they'll laugh like the devil at all of that, and they'll say, there's no problem, even random oscillations, we can control straight away with our theory, but they put the 2 together as one field. Fortunately, their results of their control theory, which is far superior to ours, are now available in books in the West. We have a few people now who understand and are trained in the Russian system. So we would jump all that other stuff and go direct to the Russian control system and use that to begin with. Once we have the math models, we have the phenomenology fitted to it, and we have the ability to design and build and scale up, and it'll work that way with just minor tweaking, at that point we're ready for production and marketing. We're not right now. We are ready for the final stage of development to go from a lab bench experiment, working, successful, to the pre-production model ready to go into production engineering and production. The beautiful thing that we have a recognized, proven, certified mechanism which does re-gauge that space around where the Aronoff bomb is effect, and it's in the literature and proven. I don't have to reprove it. So, is it scientifically proven? Yes, in the literature. Will the scientific community accept it? No. Because what they do is they say, oh no, it's a power problem, that's electrical engineering. Electrical engineering says you can't do that. Now, they have been using the Aronoff bomb effect since 1959, but they've been paying for it like in little toroidal coils, not getting it free. And the other thing is, the people that have been using it are people that do itty-bitty quantum mechanical experiments. Nobody has thought to use it in power.
So your general operational control is the square wave or the cycle.
It's not exactly a square wave. It's a sharp rise time, sharp decay time. That's adjustable. The pulse width and the pulse repetition rate are all adjustable. There are many adjustments you can make. Everything affects this thing that you adjust.
What I'm asking about is your only danger is melting the insulation.
No, the real problem is not that. We can solve that just with the rise time, decay time. And we've got that problem solved. But the problems that are difficult, really difficult, is where you have all these high nonlinearities and feed forwards and feedbacks. You actually have a very dense signal environment right inside this thing. You have to measure individual signals in a dense signal environment. That's a tough job.
But in theory, you could build a system where all of this is automatically calibrated.
Once you have done the technology and the modeling, yes, you can do that. Now, if we want to close loop this system, let's take this same system. Let's put a real efficient. So efficient, I'm going to say it's 1.0, because we can get 0.9 if we pay for real good guys to do it. But for ease of calculation, let's put a feedback system on this thing. And let's say it's 1.0, it's 100% efficient. So I don't have to worry about that figure, because this 5.4 might be bigger, see. I'm using my 3 here with what we really got of it in practical after we got the shaping for loads. I'm paying that price. The actual output is 5.4, but I'm only charging the 3 because I'm willing to pay. I know I've got to pay that conversion price. It's not going to be that much, but I'm going to be very conservative here. So I'm going to pay 2.4 points and leave my 3. Okay, with this 100% or nearly 100%, I'm going to feed one part back. I'm going to leave 2.0 as the output. But the one part that I feed back now can remove my generator. And it's furnishing, for part of its output is furnishing that input. This is clamped and governed, so it's not going to run away. Okay, I'm now reduced to 2.0 from what I had been doing that was all the way up to 5.4. But that's free energy. It's coming out, it's coming right out of the environment, and it's continuing, and I'm not paying anything for it. It now is the equivalent of a solar-powered system, or a hydroelectric powered system, or a windmill powered system. And its COP now is infinity with a closed loop. Once I disconnect that generator, once I get it going and stable and operating under load, but all the controls working, everything's stabilized out, I disconnect the generator. That's Krone's condition, by the way. Krone laid that down in 1945. The great Gabriel Krone, who built a successful negative resistor and self-powered the network analyzer at Stanford University, laid down the condition for making it self-powering. So we're just using Krone's method. I am not free to name the university that's working with us. We are working with a foreign university. We had to go completely out of the United States before we'd find one that, in addition to non-disclosure, would sign a non-circumvention agreement. An inventor can't work under just non-disclosure. He's also got to have non-circumvention. You must not say that I'm going to change some coils and all and patent this thing all around you and run off with it. So if you have a non-circumvention agreement, you can work with them. We could find no U.S. universities that would work with us under non-circumvention, because they are charged with making patents, and they'll try to out-patent you on your own device. We found one in a nice foreign country, and we're very satisfied with those people, and we're working very close with them. They are deliberately, to be purely scientific, staying independent of us. They will not accept funding from us. They are using their own funding, which is meager, but they're using their own funding so scientific independence is being maintained. The things that I've described we have to do before we get to ready for pre-production engineering is a minimum of 1 year and a minimum of $9 million. Any way we price it, when we get the people that we have to have, the specialists, the equipment, the new test equipment, the new methods of test, new test guys that do that kind of testing, it's an expensive proposition. It's not cheap. But that's peanuts compared to what we're spending on hot fusion, or what we're spending on all kinds of things, fuel cells and things like that. They're spending billions of dollars here. This is scalable. This is doable. Now, there's one other way we could do it. We could sell stock and raise stock from investors, and I could make all kinds of songs and dances, and so could the rest of our group. We prefer not to do that. We are seeking one single risk venture partner that we can work with. It's an honest group or people. We can work out a mutual arrangement for both our benefits, and then we can get on with the job. Now, what we refuse to do is turn control over to it. We could have gotten funding if we would surrender control and guarantee it never makes the market. We have no intention of doing that. So we will stumble along until we get funding that we can still guarantee it'll go to market, or we can give it the best shot that human beings can give in the world. We're not going to take something and park it on the shelf and it's just one more system that never is going to make it. Some of the breakthroughs in the past have been deliberately suppressed. I will name a few. For example, Nikola Tesla had one. Basically, his big magnifying transformer that he had on Long Island was such an over-energy system. The way that one apparently worked is he got the entire Earth itself in resonance. The crust of the Earth, as you go down in there, is made of highly nonlinear materials, particularly when you get down to the perovskite or whatever you call that stuff. And it will act in the bulk even, it will interact in a sort of a nonlinear optics fashion. It will do phase conjugation. And so eventually what it does is everything going on is feeding energy into the Earth starts to feed energy into that wave that he created. So he gets a lot more energy in his resonant wave fed from outside, from the environment in the interior of the Earth. And that's the way he built up a humongous wave of energy. His idea was you could then put in a tap on it anywhere else on the world and extract it free. And of course J.P. Morgan's take on that was, that's foolish, you can't put a meter on it. So that actually doomed much of Tesla's career at that point, when Morgan found out that Tesla was going to produce the energy freely. Small cost here at a central location, everybody else could tap it for free. It wouldn't have powered the whole world today. It would have powered much of the world in those days. Tesla also, we're pretty sure, put a system in a car and ran a car on it. And the reason we're pretty sure is his nephew, who rode in the car with him, is still alive and can describe the incident and how the engine had no gas, no input of power, and would still run once Tesla got it started. And we know it's perfectly possible. Tesla apparently knew how to use this giant negentropy process that's universal everywhere. Energy is free for the taking from the vacuum, anywhere you want it. We just have to learn to use that. And before Tesla, there was an American engineer named Stubblefield. And Stubblefield found out how to take the energy out of the Earth and take it out of what's the natural potential. Stubblefield had found out how to manipulate that kind of thing from the background potentials that are there and limitless, that normally we just see a big zero or almost zero. We'll see, a tiny bit of, 1 volt or 2 volts or something. It can be turned into much stronger currents and power, and he found out how to do that. And as a matter of fact, Tesla visited him. And there's at least one picture of Nikola Tesla in a group visiting Stubblefield. So Tesla was familiar with Stubblefield's work.
Stubblefield knew what he was doing, and he knew what radiant energy was, and he also probably had the first pulse motor. I did all those experiments. Stubblefield was just a farmer who would just find his way down to the local railroad station and read publications from Electrical Wireless. So he had no formal, really, background in electricity at all. And when you don't have the formal background, things work. In other words, here's a guy that invents an earth cell, lights carbon arc lights, runs motors, has the telephone running on no energy whatsoever except for what's in the ground, and is doing this for miles. The technique was that the earth supplied all the energy that was needed. And since you're modulating the radiant energy, the voice appears at the other end. He did it by sticking 2 rods in the ground, and that powered his telephone. That was it. So he built a battery, what he called an earth battery, which was copper and iron wire, and he actually put this battery in the ground, and he used that as the source for his telephone system. So one earth battery at this end, one earth battery at that end, right? But you see Stubblefield in the pictures and everything as here's his earth battery, here's his transmitter, okay? And his kids, he's out, a mile out, he sticks 2 rods into the ground. The guy picks the receiver up, and there's his kid playing the harmonica on it. Now, where'd the energy come from? They were using carbon microphones, and they were using, induction coils as a transformer, and real simple stuff. I mean, the guy had a telephone system that virtually was penniless to operate. Shame on you. Right. We can't charge you, so therefore, let's get rid of this telephone system. The guy, from what I understood about everything that I researched on him, he had a way of detecting if you were coming through his cornfield. He knew exactly what direction you were coming from. Now, what science is there that allows you to do that today besides the science of our technology, which is, gee, you want to see the guy coming through the cornfield? Here's an infrared camera. But it's using a battery and wasting energy. Stubblefields didn't do that. Just a little ball swung in the direction the guy was coming from. Did it all by itself. Oh, this is in the 1800s. Around the time of Tesla. Tesla's standing in the picture. Why is he standing there? Why is he at this demonstration? The thing is, later on, Tesla develops the term radiant energy. So did Stubblefield stumble upon something that absolutely had to be squashed right then and there because of the phone system? Remember, we had the telephone. We had the telegraph. Look at the telegraph systems. Copper and zinc plates in the ground, one overhead wire, and they magically powered themselves for years. And sometimes, at the right moments, the telegraph operators could be electrocuted by the jolts that came off these things. Look at Miyuchi before this. Miyuchi develops radiant generators where he gathers the energy right out of the air by a process of coating his wires. And the only reason Miyuchi develops this is he had to keep in communications with his wife because she was sick. She couldn't get around, so he develops a telephone system before Bell. Through the ground, through the wires, right? Earth batteries, just big plates, powering this telephone system that he kept in communications with his wife. Was an excellent chemist. Develops a coating for a wire that he strung outside in the air, and it gathers the energy in the form of electricity. Tesla's not in this picture standing with the whole gang, including George Westinghouse, for no reason. They're all there present in the picture. And the funny thing about this is this guy's a farmer. This guy's a farmer, and he only knows what was the proposed theory at the time. And he was interested in electricity because, now see, there's two different things here. You see, we got to define the electricity. Stubblefield's electricity was radiant or etheric electricity. There was no form of current in Stubblefield's electricity. You never see in any of Stubblefield's demonstrations a current meter because there is no current. Negative energy is radiant. You know, when he talks about negative energy, he's talking about energy that's opposite of the energy we know. These are all negative energies as far as the energy that we have. There's no mysticism here. Negative energy is radiant energy, or what Tesla termed as radiant energy, or what is termed energy from the vacuum.
John got into radiant energy. He got in eventually into Stubblefield's work, and he was the only person I know of to this day. I'm not saying somebody else may not have done it. I'm saying he's the only one I know of that actually replicated Stubblefield's work. And that is something else, because Stubblefield was a phenomenon. And John uses the same term for that part of it as Tesla did. He calls it radiant energy, just like Tesla did in his radiant energy patents. And what he means by the term radiant energy is a combination of energy while it's still in the primary state in space, hasn't interacted with charge or mass yet. And he's also including negative energy in it. It can be either positive or negative. His term radiant energy actually means precursor state energy. The same thing the Russians went to their great system and classified so high in energetics, you see. He's doing Russian energetics on the bench, that's what he's doing. But completely independently with his own discoveries. So when he uses the term radiant energy, and I'm using radiant energy, that's what he's using. He's using the next step just past what we're doing in electrical engineering.
In other words, it doesn't follow our conventional science. It can go through things that are dielectrics. Instead of wires, it may appear in a dielectric. It can melt plastic. It can use plastic as the conductor.
Stubblefield was able to take the energy out, and he was able to cause this energy to light the sky around his place, illuminate the trees. The light would originate in the ground, and the ground would radiate. And when he died, vans and folks came up to his small place, and everything in there electronic or electronic looking got moved out of there and taken. So they buried that one when Stubblefield died. And you had Tesla. You had several other people obscurely between Tesla and Moray. The next one of great magnitude that, you know, really made the papers and all is, I think, Moray, although you can find a couple of others in there too if you look. And a succession of people came along who found different ways to extract the energy from the vacuum or to take it from the background potential, whatever you want to call it. And in every case, they were suppressed. T. Henry Moray was inspired, of course, by Tesla's work, and he demonstrated so many times to so many scientific and engineering groups and people who were skilled in the art. There is absolutely no question that T. Henry Moray had a system that produced about 50 kilowatts out of a 55-pound box. This is well established as you go back and look at all kind of certified tests and everything else that he did. There's all kinds of skullduggery that happened there. I don't think T. Henry Moray ever got a decent chance to ever do anything with that. The Russians even tried to kidnap him at one time. It reads like a James Bond movie, but it's real. It really happened, and it really happened here in the United States. This was before the war. This was in the 1930s. In the same general period of time, one of the greatest electromagnetic fellows we ever had, scientist, was Gabriel Krohn. And Gabriel Krohn invented a true negative resistor working on a Navy contract for Stanford University. He was never permitted to reveal the exact way that he constructed his negative resistor. But I used direct quotes where he, in fact, said, we have a negative resistor and we can disconnect the generator from this network analyzer when we got negative resistors in there because they will power the circuit. So that one was, in fact, suppressed. I don't know whatever happened to it, but it vanished. And he never did reveal the secret of what he called his open path, connecting any 2 points in a circuit. But it is in the literature and is well documented because he was one of, perhaps the leading electrical scientist in the United States at that time. Well, there's another one that went down the tube. Various and sundry people have made casual ones from time to time over the years. I'd estimate probably 50 different inventors have casually invented something. Even if they didn't understand it, they did get it to go over unity. We're never able to get anything done with it. Most of the time they incurred a lot of enmity from the scientific community. Sometimes were really hounded, and sometimes were just very naive. Sometimes very naive. They fell in. Some of them fell into arrangements with people who were interested in selling stock and didn't care where anything worked or not. And then we have had charlatans in the area. Probably the best documented scientifically over unity systems, self-running, self-powering systems, were developed by the Russians before World War II. It's in the French scientific literature, and it's also in the Russian scientific literature. The papers are there. I quote them in many of the things that I published. And you can go check the papers. The theory is there. Many papers are published on this in the Russian scientific literature. They built what we call parametric oscillators. They have an oscillator going and they change in the middle, they switch the actual inductance or capacitance or both of the things so that it becomes a self-oscillation device. And they reached, you know, goodly power for those days of 50 and 100 kilowatt devices. They found they had to have nonlinear loads because if they used just a standard resistor linear type load, the thing would self-oscillate, and it had enough positive feedback it would continue to build up and would eventually destroy itself. With a nonlinear load, it would reach a plateau and operate at that plateau. That work is well documented. I have no idea how that got suppressed. Probably once Russia was attacked in World War II, the war was so awesome and so terrible, so many casualties and so much massive effort by the Russians, I think it just got swamped out of there. But the work is still in the literature. You can check the papers, and they're for real. That's real work by real physicists in a couple of the leading institutes in Russia prior to the war. And there's quite a few of the papers in both the French scientific literature and the Russian scientific literature. Lethal force is used. I worked with an inventor, for example, the Sparky Sweet is quite well known. And He was shot at once with a silenced rifle a sniper rifle from about 300 yards. The only thing that saved his life was he was an old guy and very feeble there towards that part of his life, and he was stumbling as he coming up the steps, and he fell down. He just flat fell down on the steps, caught his foot and fell right forward, and as his head went forward, the bullet went right by where his head was. And of course the assassin was never found. So there are many cases like that. Some are killed. I believe Marinoff, I believe to be a kill. I don't believe Marinoff jumped off a building when he was excited on the way to talk about his invention and so forth. Gave no indications of it. If I can believe the reports of the people who visited where his body lay on the pavement glowed. And there's only one weapon on earth that will kill a human body and leave where it lies on the cement, let the cement glow under it, and that's a longitudinal wave shooter, what's called a shooter. So I believe, my personal belief, I can't prove this in a court of law, I don't intend to try, but my personal belief is that Marinoff was killed. He was probably killed by either the KGB or one of their agents from one of the other Iron Curtain countries, killed with a shooter and thrown off the building to make it look like suicide. The police probably knew about it. That's why they let the body lay so long before they moved it. They didn't want to tangle with the longitudinal waves from it. So yes, there are some rather bizarre things that have occurred to some people.
I forget now what I was looking for that day, but the guy ended up wanting to know what I wanted to use it for, and it had to do with free energy. And so at that point, he says that he knew firsthand, this is the exact words, he knew firsthand that all the oil companies employ groups of engineers whose main task is to evaluate every energy-related idea they can find. And he said when they find one that they like, they will make the guy an offer. And their attitude is that usually the inventors are short of money. They like to invent, but they don't know how to make money. And so they'll typically offer them $40,000. If that's not enough money, they'll keep raising the offer until they find the guy's price. And then they will buy it, and then they will bury it. Now, just coincidentally, this one little machine that I've personally tested that put out 4 watts of power, Don Maxwell was actually the inventor of that thing. Don lived in Dallas, Texas at the time that I met him. I'd been working with him for quite a number of months, trying to build hardware for him and so forth. And I get this phone call from him one night. He's very agitated or excited or whatever in this phone call. And he had just hung up the phone from talking to a guy who'd called him. And the guy said, I work for Atlantic Richfield. We know about your device and we want to buy it. And the guy began to tell Don about everything they knew about him. The fact that he stored information on his computer and little details. Some of the details could have only been known to somebody who'd been listening to phone conversations between me and Don, because they were just, we're just talking details about something. And then the guy went on to tell Don about several different inventors around the world who had devices. And in each case, the guy told Don how they intended to stop the use or continuing work on each one of these devices. Yes, very specifically, this guy by name, and they weren't just talking generic devices, they were talking name. So I listened to all this, and after we hang up, I sit down and I write down on a piece of paper everything that Don told me. And then I typed it up, sent it off to him, and said, is this what you said? And he only changed a couple words in it. And so the only thing that I could think of to do at that point was to send everybody whose name was mentioned a copy of this. As a, hey guys, heads up, Well, it turns out that I knew who all these people were. Well, the guy that told me about this first person has visited this guy's house and learned how to build these things from him and was in the process of building them. Well, it was the second person whose name was told to my friend Don as the person they were going to stop. And the way they were going to stop that project is they would place something near where the machine was that would cause the machine to not operate when he wanted it to operate.
This is early 70s. By this time he had built EMA-4. EMA-4 was a full-sized power plant, 80 horsepower on the dynamometer. Sitting on the rack, he would quite often show it with an automobile transmission bolted to the back of it. It ran on 4 large storage cells, which the system would keep fully charged at all times. So he had come a long way. He was clearly demonstrating a form of energy which you can't fake easily by lighting light bulbs underwater without being shocked. He was showing a dramatic gain in mechanical energy derived from his circuit motor combination. And he was giving demonstrations, and people were giving him good press. In 1974, about a year after all this good press started happening, for no reason that can be traced to any inappropriate activities by Gray from a business point of view, the Los Angeles District Attorney's Office raids his lab. They pack up all his business records, they pack up all his working models, and take it away, haul it away. They spent the next 8 months contacting all of his stockholders and everybody, trying to get them to file charges for fraud against Gray, because obviously he was demonstrating something that just the laws of physics says impossible. Obviously he's cheating you. None of them would press charges. So in other words, when the DA went into the office, they didn't have a case against him. They had no one who had filed a complaint. They had a warrant, but they had no complaint. To this day, no one knows what initiated the raid, because no one who was a stockholder or involved in the business in any way filed a complaint. In other words, as it's stated in the articles, the LA District Attorney's Office acted unprovoked. At the 8-month point, they could get no one to even file a complaint to back up their case, at which point they charged Gray with fraud and grand theft. But they had no evidence to support it, and ultimately those charges fell away too. But not before a lot of time was lost and a lot of money was spent defending yourself against this nonsense. Ultimately, the end of this witch hunt found a number of minor SEC violations. He paid a fine, and the case was dropped. After the charges were dropped and the criminal case was dispatched, Gray was never able to get any of his business records or any of the working prototypes back from the DA's office. None of his personal property, corporate property, was ever returned.
There's even a little evidence, and I don't know really how to put this in perspective. We had one friend, for example, that we worked with very closely, who built practical over Unity systems. He demonstrated at a conference, for example, an 8-kilowatt system, and then very mysteriously he and his whole family disappeared. We have found out since, in fact not long ago, that he's still around, and he's doing very well because he was attired in a very expensive suit and a very nice automobile. But he and his family are okay, even though they disappeared back there. But here was a successful unit that just flat disappeared off the face of the earth. Now I assume, rightly or wrongly, It has to either be for the great financial empires, or it has to be for some kind of black project that somebody needed a power system that would power itself in the load. And they classified it. Whatever it is, I don't know, but whatever it is, the survival of humanity itself and civilization itself is now at stake. And I really believe through the auspices of the U.S. government, regardless of what that kind of program in it anywhere may have, we must bring it forward to save ourselves and save the earth. If we don't, we can keep it secret, or we can keep it in the control group hands, and we shall all go down to oblivion. I prefer not to dwell on that, try to get by as much of that as we can and try to dwell on the science. The only way we're ever going to beat all of this stuff, we have to convince the scientific community that there's real science here. It's really a good theory. It doesn't violate physics. It doesn't violate thermodynamics. And it's experimentally proven. And this is the thing we have to concentrate on and get through. Because if we ever get the scientific community turning those young grad students loose, they can plot and scheme all they wish to. They'll roll over them just like a steamroller. And that's what we've got to get going. We're trying to communicate the truth as fast as we can, as massively as we can. And that's the best we can do, unless we can get the government to move. If we can get the government to move, they can cut through all of that by simply issuing the order to do it. And that's what it's going to take. Well, not just us, there are several other inventors and groups in the same area and have systems that work. We are not the Lone Ranger here at all. I want every system out there that works and is real going. We need everything we can do. Now that's my personal view. A lot of folks think that we're going to be able to just to stagger on with the way we're going, polluting the whole planet, increasing the electrical demands everywhere. Everybody wants a modern life. They want to get out of the mud and the slime and everything and have lights and have, things that are powered and have industry and jobs and homes and schools. These are common strivings from the human heart. And to try to do that the way we're doing it will destroy the planet, and we will forcefully destroy each other. It seems to me we just ought to be wiser than
that. Late in his term, President Bush acknowledged the need to move beyond oil.
By applying the talent and technology of America, this country can dramatically improve our environment, move beyond a petroleum-based economy, and make our dependence on Middle Eastern oil a thing of the past.